All of you should have received stereo glasses. Place them carefully over any glasses you normally wear. Start at the top of the test chart and slowly read down as far as you can. Mars in 3D explores the three-dimensional character of the surface of Mars as revealed by the Viking cameras. Since there's nothing exciting or flattering about pictures of your narrator in stereo, the narration scenes are presented monoscopically. The first stereo scenes were taken by the Viking orbiter cameras. The initial orbiter task was to select a safe site for the lander spacecraft, avoiding the difficulties presented by the Mars terrain. After the landing, the orbiter served as an invaluable relay station, passing each day over the lander horizon. Following the orbiter pass, signals stored on its tape recorder were sent to Earth to be received by one of three 64-meter antennas spaced around the world so that one of them always has Mars in view. As the orbiter traveled an elliptical path around Mars, ranging from several hundred to many thousand kilometers above its surface, numerous stereo image pairs were acquired, the spacecraft traveling hundreds of kilometers between each image of the pair. This large separation exaggerated the three-dimensional appearance of surface relief. Features appear higher or deeper relative to their horizontal size than they actually are. This effect is dramatically illustrated in these first stereo scenes taken at the Chryse Basin. The 10-kilometer diameter crater appears much deeper than it actually is. Subtle details of the surface are also emphasized. Note the edges of the teardrop-shaped plateau. Features such as this were apparently formed a long while ago when a catastrophic flood of water rushed over the surface. The crater protected the plateau from erosion as material in the surrounding region was removed and carried downstream. In order to understand the possible ancient sources of this water, stereoscopic images were acquired of fluvial channels leading into Chryse Basin. Separate channels, clearly seen in three dimensions as winding depressions, cut through the older, more cratered terrain located to the west of Chryse Planitia. The stereo images make it possible to calculate the gradients of these channels and the volumes of water required to create these features. The rough appearance of this surface led to the rejection of the pre-planned landing site. A 2-week search began and a safer region was located several hundred kilometers to the northwest. We come next to an area north of the large volcano Olympus Mons. Because the two images were acquired at different times of the day, the shadow positions make it difficult for the stereo viewer. As we move north, the shadow problems become less pronounced. Extensive faulting caused numerous offsets in the surface topography. Large blocks are either lifted or dropped relative to the surface. The smooth portions are more recent volcanic flow, filling the low areas of the scene after the faulting had occurred. Three-dimensional imaging of the surface allows detailed mapping of the faults and structures such as these. Mapping the various faults and determining the time order in which they occurred makes it possible to unravel a considerable amount of the volcanic and structural history of the region. The most dramatic three-dimensional orbitocene are the massive canyons extending 4,000 kilometers in the equatorial region of the planet. As we move across the floor of the Candor Chasma, we suddenly come upon the edge of the canyon in spectacular relief. Stereoscopic data is essential for the interpretation of the strange light and dark regions on the floor of the canyon. Near Use Chasma, we look down into a branch of the main canyon. This side canyon is as large as the Grand Canyon on Earth. The canyon walls reach 4 to 6 kilometers above the floor. Widening seems to occur by sapping. Material falls from the walls to the bottom of the canyon and is carried away, on Earth usually by a river. On Mars, the process of removal is unknown. These next scenes are of the Viking lander taken at the Jet Propulsion Laboratory in Pasadena, California. Here, a full-scale spacecraft with an operating soil sampler and 2 operating camera systems was installed. Commands to be carried out on Mars could be duplicated to aid the planning activities of scientists here on Earth. In the background is an artist's concept of Mars, painted prior to landing. The lander spans almost 3 meters and reaches 2 meters from the footpads to the top of the large antenna. The bottom clears the surface by just 23 centimeters. In front, we see one of 3 terminal descent engines, ignited when the spacecraft is traveling about 225 kilometers per hour. They slow the lander to 9 kilometers per hour by the time it touches the surface. The final shock is absorbed by the compressible honeycomb aluminum in the 3 landing legs. The 2 cylindrical turrets I pointed out earlier house identical cameras. Separated by 0.8 meters, they view the Martian scene from a vantage point 1.3 meters above the surface. Protruding on the right is the meteorology boom. Every day, the measurements of this Martian weather station are transmitted to Earth for study. Between the 2 cameras, we now see the surface sampler arm with its 10-foot retractable boom in its initial stow position in the gold shoebox-sized canister. On either side of the top of the lander are the covers that surround the radioactive isotope thermoelectric generators. These use plutonium-238 to provide energy for the lander. The boom is constructed of 2 stainless steel pieces of foil welded together along the edges. When the boom is extended, the steel layers form a double curved rigid tube, much in the same manner as an everyday measuring tape. The circles below the collector head are magnets mounted on the backhoe to study the magnetic properties of the soil. With the aid of a computer-based ranging system, the images acquired by the 2 camera eyes on Mars were used to create a model of the Martian terrain in front of the test lander you were seeing here at JPL. This model was used to generate arm commands that place the arm in precisely the right position to acquire samples, dig trenches, and roll rocks. Move your head slowly from side to side, and you will observe an interesting effect. The arm extends the commanded length and then lowers itself to the surface. Using information from computer-generated vertical profiles of the surface, arm commands instruct the collector to push forward to dig and acquire a sample. The head at the end of the boom can lift 5 pounds. The cover in the test lander doesn't quite close, and a great deal of the sample is lost. We see the mirror on the side of the arm. This allows the cameras to look underneath the spacecraft. The arm retracts and then rotates to deliver handful-sized samples to the 3 inlets on top of the spacecraft. One leads to the chromatograph, which separates different organic molecules into groups, which are then drawn into a mass spectrometer. The output electrical signals produced are recorded and sent to Earth to complete the organic chemical analysis of the Martian soil. Another inlet system distributes its soil sample to 3 biology experiments that search for signs of living microorganisms. A labeled release experiment looks for signs of metabolism. The pyrolytic release looks for organisms that function by a process that assimilates carbon from the carbon dioxide-rich Martian atmosphere. Photosynthesis would be an example. The gas exchange experiment detects organisms by measuring changes in gases in a closed environment. We see the sample delivered to the 3rd inlet on the right, where it enters the X-ray fluorescence experiment. Different atomic spectra are emitted for each chemical element in the sample. Here again, the electrical signals are transmitted to Earth for analysis. Also on top of the lander are 3 test charts. 2 can be viewed by each camera from a distance of about 1 meter. The gray and colored patches and tri-bars aid in calibrating the camera. The grid allows us to study movement of dust. Next to the central test chart is a microdot emblem that contains the signatures of 10,000 people who contributed to the success of the mission. Above this emblem is a magnifying mirror that aids in viewing the magnetic particles on the backhoe. Inside the camera protective housing, a mirror gathers light from each point of the scene on Mars and directs it to an array of 12 photosensor microdiodes. Some of the diodes gather light from a 0.12 degree aperture, which may have red, green, blue, or infrared filters. Others have a 0.04 degree aperture and take high-resolution black and white images at different focal distances from the spacecraft. An electrical signal proportional to the incident light is sampled and transmitted to Earth as a binary string of 6 zeros or ones. These instruct the ground reconstruction equipment which of the 64 levels from black to white is to be assigned to that one element of the image. We look through the double protective window to the nodding scan mirror. Each time it nods downward, it gathers light from a vertical line of the scene on Mars and creates 512 picture elements or pixels to be sent to Earth. The mirror, having nodded up and down, is ready for the next vertical scan line. The camera rotates and steps clockwise and azimuth, separating each scan line by 0.12 or 0.04 degrees depending on the diode being used. By command from Earth, we determine the central angle of the nodding mirror and the start and stop values of the azimuth stepping. In this way, over a period of time, we accumulated pictures ranging over 342.5 degrees in azimuth and from 40 degrees above the horizon to 60 degrees below. Joining individual camera events occurring on different days throughout the mission, using both cameras on each spacecraft, computer-generated mosaics were made, which are the basis of the stereo movies of the lander scenes. Each 342.5 degree panorama incorporates approximately 15 million picture elements or pixels. Because of the large 0.8 meter separation between the 2 cameras, the images have an emphasized stereoscopic effect. The scene appears to be miniaturized, and there is a large parallax in going from the horizon to the near field. The movie has been made to make it easiest to achieve stereo fusion at the horizon. Once you get accustomed to the image, you can move slowly down and retain the stereo effect. We begin our 3-dimensional tour of the surface at Chryse Planitia, the Viking 1 lander site, 22 degrees north, 48 degrees west. We're 25 seconds after touchdown in the afternoon at 16:13 after local Mars midnight on July 20th, 1976, Camera 2 on Lander 1 was unstowed and took the first pictures of the surface of Mars. Concentrate first on the horizon. The prominent rock on the ridge is an ideal starting point. Relax your eyes until you begin to see the stereoscopic effect. After achieving fusion, slowly move your eyes along the horizon. Now shift your attention gradually to the foreground. As you do this, you should be seeing a series of ridges and rocks. Many people have difficulty fusing the bottom half of the image. Don't feel left out if you can't see the nearest rocks. Enjoy the more distant vistas along the horizon as we take you on a three-dimensional journey over the surface of Mars. The present surface of Chryse Planitia was formed long ago when volcanic flows and lavas buried an even older surface. However, as we move over these volcanic plains, we see little that suggests lava flow. Instead, the most abundant features we see are loose rocks lying about on the surface, fractured and dislodged from the underlying bedrock by some process of erosion. At both lander sites, we now believe that asteroid impacts are the major process creating loose rocks. These impacts form craters, fracture the bedrock, and eject loose blocks at high velocities in all directions. Photographs from the orbiters show that there are numerous small impact craters surrounding the Lander 1 site. The loose rock here may have come from an impact crater just over the horizon in front of you. If we could rise up and peer over this ridge, we would find ourselves staring into the interior of a shallow impact crater. Nestled in a small depression, you can see what appears to be a smooth, bright feature. This is a small, isolated deposit of dust material, which has been transported and deposited by the Martian wind. We shall see other more extensive areas of drift material behind the lander. One of several outcrops of ancient volcanic flows is visible in the midfield. Horizontal layers are clearly seen. A curious black linear structure extends from the lower right to the upper left. This structure is possibly a fault or a fracture, and can be seen in both the bedrock and the adjacent landscape. About 10 meters from the lander, at the left of the scene, may be seen several accumulations of drift material. Exposed ridges are visible on the surface of the drifts. These are believed to be deposition layers within the drift material. As the wind erodes the drift at an angle to the deposition layers, the edges are exposed. This is the best example at the lander site that shows that the drifts are being eroded rather than being slowly transported across the surface as a unit, in the manner of moving sand dunes. The nearest rocks visible in the foreground are only 4 meters away. The highest point on the distant ridge is 5 meters above the lander. A sequence of smaller ridges at intermediate distances can be seen between the foreground and the horizon. In order to appreciate the usefulness of three-dimensional information in understanding the scene, try closing one eye for just a moment. You are looking to the southeast of Lander 1, directly to the front. The images comprising the mosaic were acquired around 7 in the morning local lander time. The sun is 20 degrees above the horizon to the upper left of the scene. In addition to the bright drift area shown earlier, 2 additional isolated drifts can be seen on the right side of the scene. In the preliminary imaging sequences made prior to touchdown, relatively little time was allotted to the areas behind the landers, since most of the surface is obscured by parts of the spacecraft. However, as we see in this scene, some very spectacular three-dimensional images were acquired of features behind the lander.
A sequence of ridges can be seen extending to increasing distances. The far ridge is over 100 meters distant. The nearer ridge is only 20 meters away. Many people have difficulty achieving a stereo effect because of the discontinuity and parallax between the nearer and farther ridge. The effect is called jump fusion because the eyes must jump between the front and distant ridges. Fusion may be difficult or impossible to achieve for both ridges simultaneously. As we look due west, we see an additional ridge spaced between the previous two ridges. The near ridges are partially blanketed by dust which has been swept over the surface from right to left by the prevailing winds in this region. The prominent block on the hill is 1 meter across. The distance which the cameras can see is determined by the height of the cameras above the ground, the height of objects in the distance, and how the spacecraft is situated, on a hill or a depression. The cameras are 1.3 meters above the surface. If the lander was sitting on a perfect Mars-sized sphere, the horizon would be about 3 kilometers away, and objects there about 2 meters in size would be one picture element. However, the lander is apparently on top of a slight rise, thus significantly increasing the distance we can see. The most distant features seen by Lander 1 cameras are these light hills about 8 kilometers away, barely visible beyond the near ridge. The distance to these hills is known because they can be seen in both orbiter and lander images. Also visible in both lander and orbiter images is the ridge now entering the field of view. This has been identified as the right rim of an impact crater 500 meters across and just over 2 kilometers away. Additional hills are visible to the northwest. As before, there is a nearby ridge which may create some problems in obtaining stereofusion. On this ridge there are numerous larger rocks interspersed with an extensive blanket of drift material. These rocks are believed to have originated from still another impact crater. The drifts you are now seeing are the edge of a field which extends more than 1/3 of the way around the lander. Perhaps the distinction we previously made between sand dunes and dust drifts needs further clarification. The word dust implies a smaller grain size than sand. The word drift implies that the material is being eroded and sculpted by the wind, rather than being continually moved across the surface. In sharp contrast to these drift accumulations, the area south of the lander is almost devoid of dust. Based on the eroded appearance of the drifts in the rest of the scene, it is believed that similar drift material may have blanketed much more of the scene than it does now. However, whether the rocks and surface seen here were buried is presently unknown. All that we see today is a variety of exposures of barren bedrock and loose block. Part of our understanding of the Lander 1 site comes from the ability to compare it to another region, visible to Lander 2 about 10,000 kilometers away on the other side of the planet, 48 degrees north and 226 degrees west. At first glance, the surface here at Utopia Planitia, where Lander 2 touched down on September 3, 1976, appears to be remarkably similar to the surface of Chryse Planitia. The predominant objects are loose rocks. Just as at the Viking 1 site, most of these rocks were originally broken from the bedrock by the impacts of asteroids on the Mars surface. The loose rocks around Lander 2 were probably derived from the large impact crater Meade, 100 kilometers in diameter, located 160 kilometers to the northeast. Far to the east is a series of hills. Their sizes and distances are unknown. Unlike the Lander 1 site, there are no clearly identifiable horizon features which can be correlated with orbiter images. Consequently, we have not yet been able to uniquely position the lander relative to the surface features visible in the orbiter images. One of the characteristics of the Mars environment is the yearly occurrence of planet-wide dust storms. These storms are viewable from Earth and have often been seen to enshroud the entire planet. Such widespread storms would seem to suggest that a considerable amount of dust is involved, and that erosion rates on the surface might be quite high. However, despite the occurrence of 2 such global dust storms during the Viking mission, the landers have only seen a general darkening of the scene. Distant features seen here, as well as at the Lander 1 site, remain visible during the height of the storms, suggesting that amounts of dust present during the dust storms may be far less than previously was suspected. Around most of the Lander 2 scene, the horizon is closer than the distant hills now in view. Nearby rises in the surface topography block our views of distant vistas. As we look at these jumbled piles of rocks and remember that the lander clears the surface by only 23 centimeters, it seems fortuitous that the lander was able to touch down without damage. In fact, the Lander 2 footpad is partially supported by a large rock. During the winter season at the Lander 2 site, the surface became covered with a thin layer of water ice. This water ice was transported northward from the equator to the Utopia region, remaining for over 100 Mars days. The thickness of the ice ranged from several to tens of microns, insignificant on Earth, but not on Mars. The close-up observation of water ice provided us with clues to the possible history of Mars soil material. One of the most puzzling features seen in the Lander 2 images is a network of shallow troughs. The most prominent is visible in the foreground of this scene. When these depressions are mapped, they are shown to form a crude geometrical pattern. Although the troughs are evidently not cut by running water, alternative explanations remain indeterminate. One possible mechanism is that they result from buried ground ice. The troughs resemble features commonly seen in the polar regions of Earth, called patterned ground. These linear depressions on Earth result from the complex distortions of the surface due to the freezing and thawing of subsurface ice. Note the variety of rocks, each type implying a different origin and erosional history. You should now remove the stereo glasses. You will enjoy the monoscopic scenes that appear with the closing titles, following this scene of sunset on Mars as seen by one of the cameras on Lander 1.